Hello, my name is Edwin Kamiringawa, and this is my assignment 3 for Engineering Technology Design project. So, design task 1 is about analyzing a three-stage operational amplifier circuit and deriving its final output voltage equation. The circuit consists of three op-amps, U1, U2, and U3. So to show the mathematical derivation, the final output Vout is a function of the outputs of the first two stages, Vout1 and Vout2. So for the Vout1, the U1 is a standard inverting amplifier. Its output is given by this. For stage 2, the Vout2, U2 is an inverting summing amplifier with three inputs, V2A, V2B, and V2C, and corresponding input resistors, R3A, R3B, and R3C. Its output is the negative weighted sum of the inputs, which can be shown here. For stage 3, which is U3 is a difference amplifier, since R5 and R6 are the only resistors explicitly labeled in the above diagram for the input and feedback, assuming the resistors in the non-inverting path are matched to the inverting path. The output is the difference between the two input voltages multiplied by a gain factor of R5 divided by R6. You can see it here. So for the combined final output, substituting the expressions for Vout1 and Vout2 into the final difference amplifier equation, the final output is given by this. The two negative signs from the inverting stages cancel out in the final summation, resulting in the positive sign for Vout2 term within the brackets. So next, I had to propose a Simulink design that meets specific functionality requirements for each op-amp stage, considering standard resistor values. So for the summing amplifier, the requirement for Vout2 was to satisfy this equation. The general equation for inverting summing amplifier is this. To achieve the positive coefficient shown in question 1, the entire stage U2 must be followed by a second inverting amplifier. Let's call it U4 with a gain of -1. So for the inverting amplifier, the requirement was to amplify a 2 volts AC signal to 6 volts AC at 50 Hz with 180 degrees phase shift, which means a gain of -3. Using standard values, I chose R1, I chose as 10 kilo ohms, and R2, which will be 3 times R1, which will give 30 kilo ohms. So for the difference amplifier, the requirement was to multiply the difference between Vout1 and Vout2 by a gain of 1.5. The difference amplifier gain is 1.5. Using resistor values, I chose R5 to be 10 kilo ohms and R6 to be 1.5 times 10 times R5, which will give 15 kilo ohms. So for my Simulink design for task 1 is as follows. As you can see here. So for my design task 2, this focuses on conditioning the raw output of the load cells to be compatible with the DAQ system that accepts an input range of 0 volts to 0.5 volts. The load cell is excited by a 5 volt DC supply. So for the sensitivity, first I determine the characteristics of the raw load cell signal from the provided data. The input full scale is 12 watts, which is 600 grams from 12 times 50 grams. For the raw output full scale, this is the answer that I got. For the raw sensitivity, I used the output full scale divided by input full scale, and this was the final result. So for the proposal of the MATLAB Simulink circuit design, this was my proposal. So I proposed an instrumentation amplifier configuration. So the instrumentation amplifier is ideal here because the load cell is a Wheatstone bridge outputting a small differential voltage on a large common mode voltage. The instrumentation amplifier provides a high input impedance, eliminating loading effects and high common mode rejection ratio to amplify the only desired differential signal while rejecting the common mode voltage. So the circuit needs to perform three key functions to match the DAQ. The first one is to offset adjustment, shift the 1.530 volts output down to 0 volts. The second one is amplification, increase the full scale span from 0.049 volts to 0.5 volts or slightly more. And the third one is high input impedance. So for this, the conditioned signal has a new span of approximately 0.49 volts. The conditioned sensitivity used output full scale divided by input full scale, which will give this as the final result. So to compare the results, uh, the signal conditioning circuit is essential. It increased the signal sensitivity by a factor of 10. As you can see, this is 8.17 times 10 power negative 4, and this is 8.17 times 10 power negative 5, showing that it increased the signal sensitivity by a factor of 10. So, and shifted the signal range from an incompatible 1.530 volts to 1.579 volts to an ideal 0 volts to 0.497 volts range for the DAQ system, ensuring an accurate and high resolution measurement. So that concludes my explanation for design task 1 and design task 2. Thank you for watching.